Okay, Chapter 1, Function Notation. Example 1, the height of a rocket at time t seconds after fuel runs out, h equals minus 16t squared plus 32t plus 48. In order to emphasize the fact that height of the rocket depends on time, a special notation, sometimes called is used, sometimes called function notation. And function notation, the height of the rocket at time t seconds after fuel runs out is now expressed h parentheses t equals not minus 16t squared plus 32t plus 48. And this is read h of t. And it looks like multiplication, but in this context it just it doesn't necessarily mean multiplication. It just emphasizes that height is a function of time. So if we want to h of negative 1, that would represent the height at time 1, and we could compute that, replace t by 1. So the negative 1 would be considered the input, and then when we plug it in and get an answer, that would be the output. So so to do f of h of negative 1, we'll have minus 16 times negative 1 squared plus 32 times negative 1 plus 48. And negative 1 squared is 1. Minus sign squared is positive. So this is going to be minus 16 minus 32 plus 48, and that's equal to 0. So the formula actually doesn't really apply at negative 1, but the equation the formula can be evaluated there, but physically the rocket is probably not on the ground at minus 1 seconds, because once the fuel runs out, the formula changes. So probably a different formula was in effect before the fuel ran out. But it's going to be helpful for the graph. It will be helpful to evaluate that point anyway. Okay, so h of 0, replace t by 0, minus 16 times 0 squared plus 32 times 0 plus 48. 0 plus 0 plus 48 is going to be 48 feet. So at time 0, the rocket is, at the moment the fuel runs out, the rocket is 48 feet in the air. Okay. And h of 1 would be minus 16 times 1 squared plus 32 times 1 plus 48. 1 squared is 1. 1 times negative 16 is negative 16. So it's negative 16 plus 32 plus 48. And that's going to be 64 feet. So once the fuel runs out, the rocket continues to go up just from its own momentum. Eventually gravity is going to slow it down and bring it down, but it continues to go up. So it was 48 feet high when the fuel ran out, but after 1 second now it's 64 feet high. H of 2, minus 16 times 2 squared plus 32 times 2 plus 48. 2 squared is 4. 4 times negative 16 is negative 64 plus 64 plus 48. And so now the rocket is on its way down. It's got to come back down to 48 feet. H of 3 rather. Height of the rocket after 3 seconds. Minus 16 times 3 squared plus 32 times 3 plus 48. 3 squared is 9. 9 times negative 16 is negative 144. 3 times 32 is 96 plus 48. And this is equal to 0. So after 3 seconds, the rocket is on the ground. We can actually plot those points. So these are the points that we computed if we graph them and plot them on the graph and connect the dots, we get a graph of the rocket. It's a parabola, which you could probably recognize from the equation. Before time 0, I put the graph with a dotted line to indicate that that's not actually in the domain. The formula really only applies once the fuel runs out, and actually when it hits the ground, the fuel no longer applies. The formula no longer applies either. Okay, so looking at this graph, we see that the height of the rocket is increasing on the interval from 0 to 1. From 0 to 1 seconds, we have a positive slope here. A little bit later in the course, we'll actually be computing that slope. It's not a constant slope. It's not a straight line, but it's a positive slope. And then at time 1, the slope appears to be 0. It appears to be horizontal, and then between 1 and 3 seconds, it appears to be decreasing. The height of the rocket is decreasing. But we'll actually a little bit in a couple of weeks, we'll actually be computing the slope rather than just looking at the sign. The domain, because of the physical situation, the formula only makes sense from time 0 to 3 seconds. So the domain is in interval notation 0, 3 with square brackets, and the range is from 0 to 64. You can, at least that appears that way from the graph. The maximum height is at 64. The minimum height is 0. So the range goes from 0 to 64 feet, and the domain goes from 0 to 3 seconds, just based on the physical situation. Okay, here's more of a sort of a generic function. I'd like to. I wanted to start with an application, so you can see how this is used. I think that the procedures make a little more sense if you understand how they're used. But a lot of the examples we'll be working with are just sort of generic functions and no particular physical context. So here's an equation: y equal x squared minus 6x plus 5. Y is here as a function of x. In order to emphasize that, we write f of x equal x squared minus 6x plus 5. The letter f is often used to indicate a generic function, and again we read this f of x. So f of 0, replace x by 0, is going to be 0 squared minus 6 times 0 plus 5, and that's equal to 5. We could also put in algebraic expressions, and we will have actually reasons to do that. There's situations where we will want to put in algebraic expressions. So we could use x plus h as our input, and in the formula for f of x, wherever you see in x, you put x plus h. So instead of x squared, we have x plus h squared. Instead of 6 times x, we have 6 times the quantity x plus h, and then copy the plus 5. And then we can expand this. This is x plus h times x plus h, and distribute the 6, be minus 6x minus 6h, copy the plus 5, and distribute the x and distribute the h here. So that we'll have x times x is x squared. The outer product is xh, the inner product is xh, so we have 2 of those, 2xh plus h squared. H times h squared, okay? Okay, so this is f of x plus h, okay? And this actually is going to be part of the procedure of calculating the slope of something that's not a straight line. This is part of what's called the difference quotient. The first term here in the difference quotient is, looks like I froze here. See if I can unfreeze. there we go. The first term of the difference quotient is f of x plus h, and this is actually the slope of what's called the secant line. So I have two x values here, x and x plus h, and the two y values, f of x and f of x plus h, and the darker curve here is the function f of x. This is a different function f of x, but I'm just, this is for purposes of illustration. So f of x plus h minus f of x is actually the difference of the y values. This is like y2 minus y1. We call this y2, y1, and x2, x1, and x2. So this is actually, it looks a little different than our usual formula for the slope, but it's actually the slope of the secant line that touches the curve in two spots. So you could have that's y2 minus y1 over x2 minus x1. Okay, and it's actually a different form of the slope. And if you simplify, you can simplify this a little bit. X minus x is 0, so you have just f of x plus h minus f of x all over h. So that gives us the slope of the secant line. And then if we take the limit as h goes to 0, if h, the secant line is going to get closer and closer to the tangent line, and that will give us the slope of the tangent line to the curve. So that's sort of the basic idea of this formula here. But anyway, we've already computed f of x plus h. That's going to be x squared plus 2x plus h squared minus 6x minus 6h plus 5. And then we want to subtract f of x, so I will just change the sign, minus x squared plus 6x minus 5. And there's a lot of cancellation. The x squareds will cancel. The minus 6h plus 6h cancels, 5 minus 5 cancels. That leaves us with 2hx plus h squared minus 6h over h. We can distribute the denominator and then divide through the h's, and we get 2x plus h minus 6. So that's the slope of the secant line, and if we replace h by 0, that actually gives us a formula for the slope of the curve at any point on the graph. Okay, so that concludes this presentation.